Hey friends, today let's look at a common problem that asks you to investigate a function and see if it is odd, even, or neither. So we're taking a look at this right now, and we have to remember the definitions of odd and even functions are the following. An odd function satisfies the condition that f of negative x is equal to negative f of x, and an even function satisfies the condition that f of negative x is just equal to the regular version of f of x. Now we'll get to what this sort of means theoretically after we've done the problem, but notice in both cases we're focusing super hard on this f of negative x, which means we're supposed to take this negative x and replace the existing x in the f definition. So let's try this, right? So we'll say find f of negative x. F of negative x is going to be plugging in negative x squared minus 8, plugging in negative x all over 7, plugging in negative x to the fourth plus 6. And let's simplify this down, right? So we say f of negative x is equal. When I square this whole thing, I'm going to square both the negative and the x. So I'll get x squared positive. Then I go negative, negative, gets me plus 8x. On the denominator, I'm going to take the whole negative x to the fourth power. So that's going to be negative 1 to the fourth power, which is 1, and then x to the fourth power, 7x to the fourth, and then the 6 is just the 6. Okay, so I found f of negative x. Now I want to compare to these things over here. I want to compare to negative f of x and regular f of x. So we can see that this is clearly not the same as that, right? Because the bottom is the same, but the numerator, I've got a negative up top and a positive down here. So I understand that this is not the same as the original f of x. So this is not true, which means f is not even. Then if I compare this to the negative version of f of x, what does that actually mean? That means I would take f of x multiplied by negative 1. Well, let's try this. If I were to write negative f of x, then that means I would take a negative 1 and multiply by either the numerator or the denominator. I'm a fan of multiplying the numerator. That would give me negative x squared plus 8x all over. Keep the denominator the same now. And we see that this, which is negative f of x, is not the same as f of negative x. Okay, so that means this condition is not true. Oh, so f is not odd. So we say that f is not even, f is not odd. So our conclusion, therefore, f is neither odd nor even. Okay, but now that we've solved the example problem, let's talk a little bit more in detail about odd and even functions. So first, let's take a look at this f of x right here, x cubed minus 4x. And what we're going to do is graph this guy. And right now, we're not going to talk about how to graph a cubic function by hand. That will be another discussion. So we just have x cubed minus 4x, hit the graph button, and here we go. All right, so currently we have y1 is the output of f of x. And then what we want to do is we want to consider y2 is the output of f of negative x. And thinking back to when we first learned about function transformations, turning an x into a negative x will just take negatives and positives and flip them. So you're taking your graph and you're flipping horizontally across the y-axis. So a neat little trick we can do in this calculator is in the y2, I'm going to say vars then go to the right y-vars, hit enter on function, and now I get a list. So I'm going to say y1 and go parentheses negative x. So what this is doing is it's saying, hey, take whatever is spit out into y1, which is the result of function f of x, but do that for the negative value of x. So this is reading do f of negative x. Okay. So if I graph this, what I should see in another color is the graph flipped over the y-axis. Indeed, we see that. Okay, so now let's take this and go, all right, what is f of negative x algebraically? Well, this means we're going to substitute negative x into all of these x's. So we go negative x cubed minus 4 times negative x, and we can simplify this. F of negative x is now equal, we take the cube and distribute, so negative 1 cubed is negative 1, so we keep the negative, and then we just have x cubed. Then here, negative negative gets positive, so we do this. And notice that this is the negative version of the original. Right? What I mean by that is, if I take negative f of x, multiply both sides by a negative 1, then I would get negative x cubed plus 4x. So I understand that this right here is the same thing as negative 1 times f of x. And this satisfies the definition of an odd function, right? So f is odd. Well, let's talk about that a little bit. So f of x is the output which we put into y1. So that's going to be the blue graph on the calculator screen. Now, if you take that and multiply by negative 1, you're taking the y value and multiplying by negative 1. So you would be flipping the graph upside down, so vertically across the x-axis. So let's visualize that. Let's pull up y equals again. And in the y3, I'm going to go ahead and graph the negative of y-vars function, y1, of x. Okay, so what I'm doing is I'm saying y3 is equal to the negative of the original f of x. If I graph this, so the blue is the top one, the red is the middle one, the black is what's being graphed here. So notice the black matches this. Okay, so let's take a step back and understand what we just showed. Okay, we showed that when you do f of negative x, meaning you take all the x values and swap positive and negative, meaning you take your graph and you flip it horizontally. That is the same thing as taking your original y value and making it negative, meaning you take your graph and you flip it vertically over the x-axis. So the conclusion here is when f is an odd function, a horizontal flip across the y-axis is the same thing as a vertical flip across the x-axis. So that's graphically what's going on. Now let's continue this same analysis with g of x. Okay, so I'm going to go back here, and I'm going to go ahead and get rid of the y3, and I'm going to go up here into y1, and I'm going to put in what g of x is. So I'm going to say, okay, that's negative 2x squared plus 3. All right, so what's going to happen, y1 is going to be g of x regular, because that's what I put in for y1, and I'm going to keep y2 with the same syntax. So what it's doing is it's saying, hey, take whatever you get from y1 except use negative x, okay? Same deal. I should get the original graph, which is a parabola. It should be an upside down parabola because of that negative right there. And I should flip it horizontally across the y-axis. There's the original graph. And there's the flip horizontally. And look, it's the exact same as the original graph. Now, I guess that makes sense. You could have looked at the original and said, well, there's symmetry. So if I flip it sideways, it overlaps on itself. Let's look at this algebraically and say, okay, well, what happens when I do g of negative x? Okay, I'm going to take negative x and substitute in for all the x's here. That's going to be negative 2 in parentheses negative x squared plus 3. So when I square, I'm going to square the negative 1, which gives me positive 1. So I'm going to get negative 2x squared plus 3 like this. Now notice this is exactly the same as our original g of x. So this is exactly equal to g of x, which would lead us to conclude that g is even. Okay, and of course, we knew this before we even did the algebra because we graphed both of these and found that they were the same graph. Okay, so if a function is even, then what that means is that you have symmetry across the y-axis. So if you flip the graph across the y-axis, it overlaps on itself exactly. Whereas in the case of an odd function, if you flip it across the y-axis horizontally, that ends up being the same thing as taking the graph and flipping it vertically across the x-axis. So it's a different kind of symmetry, but a type of symmetry nevertheless. You could say that this one has a form of rotational symmetry, as in if you take the graph and rotate it by 180 degrees, it overlaps on itself. That's a separate discussion now. Okay. But now, the third and final example, let's take a look at this one, and we will clear this out and enter 2 raised to the x power plus 1. Okay. Oops, sorry. Back and delete that. Okay. So, once again, we're going to say y1 is equal to the function h of x, and then y2 is going to be h of negative x. So what we should see is the graph of this, it's an exponential curve, and we're going to take that exponential curve and flip it horizontally across the y-axis. Beautiful exponential curve with a horizontal asymptote at y equals 1 because of this. All right. And in red, we're going to see this like that. Okay. So here's the deal. Does this horizontally flipped h of negative x match the original h of x? Well, clearly not, because the graphs don't overlap on each other. Or will this be the negative version of h of x, like we had up here with the f? Sorry, I'm covering up the negative there, but there's a negative. Okay, so let's graph y3 is equal to negative h of x, reminding ourselves that multiplying h of x by negative 1 means you're multiplying the y values by negative 1, so your graph will flip upside down. So let's do this. We'll go into y3 and say it's going to be the negative version of vars over to y vars function. And there is a shortcut for this. At some point, we'll start doing it, but for now, vars over to y vars and then function. All right, so we graph this, and in black, we get the upside down version of the original blue, right? Because this guy's in blue. If we make all the y values negative, we should flip the graph vertically over the x-axis to make that. Oh, look, they're not the same. Okay, so this and this are not the same, which means h is not odd. This and this are not the same, which means h is not even. Take a moment to internalize that. Let's do the algebra just for fun, right? So we're going to say, okay, wait, what is h of negative x? So we're going to take this negative x, substitute in for all the x's. That's going to be 2 raised to the negative x plus 1. And the question is going to be, is this equal to the original? Well, you have to sort of think about exponent rules when you do this, but there's no rule that says 2 to the negative x is the same thing as 2 to the x always. They're not the same. So h of negative x does not match h of x. Okay. That means h is not even. Internalize that. Then I ask myself, is this the same thing as the negative version of the original? Meaning I multiply the entire thing by -1. So that would be negative 2 to the x minus 1. Okay, let's just write that down. Right, so if I say, what's negative h of x? That would be negative 2 raised to the x minus 1. Is this the same thing as that? Well, once again, you have to consult exponent rules, but it turns out they are not the same. And you can easily convince yourself by plugging in some numbers, right? Let's say, plug in x equals 3. 2 to the negative 3 ends up being 1/8. 1/8 plus 1 is 9/8. Then if I say, okay, 2 to the 3 is 8. Negative 8 minus 1 is negative 9. Oh, those are clearly not the same, okay? So if any value of x yields not the same, then you would say this function and this function are not the same. Okay, so if this and this are not the same, that means h is not odd. Okay, internalize that for a moment. So h is not even, and it's not odd, so we would say h is neither odd nor even. Okay, so once all of that is said and done, we have to ask ourselves, graphically, what does it mean to be an odd function, okay? Graphically. So in all cases, the first question is, what happens when you look at f of negative x, the function with the x values flipped, okay? So that means take your graph and flip it horizontally across the y-axis and ask yourself what happens, okay? If you flip your graph horizontally and you end up with the same thing as the negative of the original, meaning you took the original and flipped vertically, you're changing the y values from positive to negative and vice versa, okay? If flipping horizontally is the, I should write this, same as flipping vertically, then you have an odd function. And this amounts to taking your graph and rotating 180 degrees around the origin and overlapping on yourself. Okay. If you take your graph and flip it horizontally across the y-axis, and you get the exact same as the original graph, as in you have symmetry across the y-axis, then your function is even. And if you don't have either of these symmetries, then you would say your function is neither odd nor even. All right, so certainly symmetry is cool, but it turns out that symmetry isn't just cool, it is super useful in math and all the applications of math. So let's just pretend, and we have an f, and it's a different f than we had before. F happens to be an even function, and we know through some, whatever, that f of 2 is equal 7/3. Now what I want you to imagine is that the process of calculating f of 2 was incredibly complicated. Right, so like imagine that, I don't know, maybe I had to calculate something for, a bunch of billiard balls and colliding and all these things, and the result was this number 7/3, and I had to use a supercomputer to do this. Okay, let's just pretend all that ridiculous stuff. Now it turns out because f is even, I can start immediately concluding things. One of those things that I can conclude is that f of negative 2 is the same thing as f of regular 2, and hence f of negative 2 is equal to the number 7/3. All right, and assuming that it was just as complicated to figure out what f of negative 2 is by brute force, right? Like imagine a supercomputer have to use all this computing time. Just because f is even, I get this like buy one get one situation, where since I know a y value here, I can leverage that information to get a y value for a different x value. Right? We can do the same thing for like an odd function. So let's pretend that g is odd, and once again, we'll just consider something where like, g of negative 3 is equal to, let's say 5. So we can use this information to conclude the following, that g of, since I know g of negative 3, I'm going to do the negative of negative 3, which is going to be g of positive 3. Since g is odd, this is the negative version of the original, which means g of 3 would equal the negative of this value. I'm able to conclude that. So, first things first, I've had students come up to me and say, well, I mean, can't I just take this negative and, move it outside so it's just negative 5? And the answer is yes, if the function is odd. This type of I can just move the negative outside, right, and get negative 5 is a property of odd functions, but not even functions. Right here, I can't just move the negative out and get negative 7/3 because that's clearly not true. Right? So we take that for granted a little bit because some functions that we're used to thinking about are odd functions and allow us to just pop that negative outside. So in this context, right, so we're sort of going along this hyperbolic imagination of it's very difficult to calculate a function output, a y value. But as long as we have an even function or an odd function, by this symmetry, we have this perpetual buy one, get one situation where if you can get a y value, you can make a conclusion about a y value for the negative version of your x value, right? And maybe a little bit sort of a stretch of an imagination, but imagine that your entire life purpose is to take a function and catalog all of the output values. So you're literally just plugging in different x's into the function and getting y values and sort of, putting them in a book for your descendants to read. No joke, this is actually what some people in history have done. In fact, I mean, you could really take some math and science research and reduce it to this idea, right? But we're just leaving stuff for our descendants. Then, simply knowing that you have some symmetry allows you to just find the outputs for like half the numbers, and then you automatically get the answers for the other half of the numbers. This is really cool. Also very useful, right? That was my promise. It's cool, but also useful. And this extends to other things. So I guess at this stage, I'm not going to try to get too complicated because this is a precalculus talk. But let's imagine, right? Pretend. So we're going to stick with the same g is odd. We'll say pretend g is odd. And we have the following. We have that g of 0 is equal to the number 7. We'll say that g of 1 is equal to 2. And g of 2 is equal to, I don't know, we'll just say 1/3. And g of 3 is equal to, we already know it's negative 5. Okay? Now, let's say we want to find the sum. So we'll say we want to find the sum, g of negative 4 plus g of negative 3 plus g of negative 2 plus g of negative 1 plus g of 0, g of 1, g of 2, g of 3, and g of 4. All right. I don't know why we want to find that. Maybe this represents some kind of like physical situation and we're trying to evaluate it. Okay. But let's just start taking a look at this. All right. So we know that g of 0 is 7. Okay. So that's a known quantity. We also know that g of 1 is positive 2. And we know g of 2 is 1/3 and g of 3 is negative 5. And that's where the given information stops. Okay. But we can get a little bit clever. We can say, well, hold on. What g is odd. So that means, right, so if I start writing these down, I can say that g of 0 is 7, right, and that g of 1 is 2, but g of negative 1, since g is odd, has to be the negative version of this number. So that means this is negative 2, okay? Now g of 2, we already know, sorry, I'm pointing at the wrong thing. G of 2 is 1/3. And we know that g of negative 2 has to be the negative version of 1/3 because g is odd. So we know that's going to be negative 1/3. And then g of 3 we know is negative 5. And g of negative 3 is the negative version of that number because g is odd. regular 5. And now we're sitting here and going, okay, so I'm going to leave this as g of negative 4 and this as g of 4. So we start thinking about how to add these things together. And we notice something. We notice that negative 2 and positive 2 will add and make 0. Negative 1/3 and positive 1/3 will add and make 0. 5 and negative 5 will add and make 0. Oh, wait, because anytime I do g of negative x and g of positive x, right, when the x's are negatives of each other, the y values are negative of each other. So if I add those two y values together, I should get 0. That means I don't even need to know what g of 4 is to know that g of negative 4 and g of 4 are the negatives, like the y values are negative of each other. So these will just add to make 0. So my answer just comes out to 7. Right? So in order to believe the utility in g being odd, I guess you had to believe that this was a useful calculation to make. But it turns out these things happen a lot in math. Summation is a very common idea. So that's all I want to talk about with this for now. Hopefully you can believe that this was both interesting and useful. And whenever you get a problem that asks you to determine if a function is odd, even, or neither, you know how to do it, right? You plug in negative x and see what happens. All right, well, thank you so much. Peace, friends.